It's time for chapter 4 in linear algebra, and chapter 4 covers the idea of vector spaces. We are not going to spend a lot of time in chapter 4. In fact, I'm only going to cover one section in chapter 4 in detail, and that's 4.9, applications to Markov chains. What you find in chapter 4 is that what they do is they take all the ideas we've talked about so far this semester and reteach them, but only in a little bit more abstract sense. And that is, instead of necessarily thinking of a vector as a collection of numbers, as a traditional vector in a two-dimensional, three-dimensional, n-dimensional plane, we're going to think of a vector space as any collection of objects whose objects behave like vectors. And there are lots of things out there that behave like vectors, and that you can kind of make a translation between vectors and those objects. And so that's what chapter 4 is about. So even though I'm not going to spend a lot of time on chapter 4, I thought I might just do a few introductions. So what does it mean to say something behaves like a vector? Well, it behaves like a vector if it has kind of this collection of properties. So you see, if you add two vectors, you still get a vector. They're commutative, they're associative, they have a zero vector and inverse vectors. You can multiply by constant multiples and still get a vector. Constant multiples are distributive and in both ways, and you can multiply, and the multiplying by a constant of 1 doesn't change the vector. So anything that hits all these properties we would call a vector, and we would say that it can be called a vector space, any collection of objects. So the objects don't have to be traditional vectors, but they behave like traditional vectors. Now, again, this semester I'm only going to focus on things that are traditional vectors, but it's worth kind of recognizing that all the ideas that we're doing can be extended beyond what we know to other things. Let me just tell you about a couple ideas, even though we're not going to spend a lot of time on them. The first idea is that of polynomials. So for example, if I wanted to think of all polynomials, say for example, of degree 3, that means we're talking about cubic polynomials, then you could think of your polynomial, for example, x cubed plus 2x squared minus 5x plus 4. We could think of this as a vector, and the way we would think of it as a vector is just think of the coefficients of the polynomial as a vector. And you'd have 1, 2, -5, and 4. And you notice polynomials fit all those properties. You can add them together and you get other polynomials. You can multiply them by constants, so they behave with all the properties of polynomials. A cool thing about polynomials, is that there's some operations that make complete sense for us. So let me just grab one of those operations real quick and show it to you, and maybe you'll find this interesting. So one operation is the matrix that looks just like this. So what if I take the matrix 0, 3, 0, 0, 0, 0, 2, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay, so now if I'm going to take that and multiply it by that matrix that I had by that vector I had a second ago, 1, 2, -5, 4. Let's make sure I did this right. Yep, okay. So now if I multiply these across, let's see what I get. So I get row 1 times column 1 is 0. Row 2 times column 2 is 3. Row 2 by column 2 is 2 times 2, which is 4. Row 3 by column 1 is also 4. Is -5, because I have those. So that ends up being our result. And let's just think about, so this is an interesting matrix, because what did this matrix do? It took the polynomial x cubed plus 2x squared minus 5x plus 4, and it turned it into the polynomial 0x cubed, which plus 3x squared plus 4x minus 5. And if you look closely, you might recognize, what is this matrix actually doing? What this matrix is actually doing is it's taking the derivative of this thing. So we can think of polynomials as vector spaces, and then we can take matrices and we can write matrices that do all sorts of interesting operations to those polynomials. For example, we can write a matrix that takes a derivative of a polynomial. And this might be a good way to deal with polynomials in some sort of computing system, and also a way to kind of think about them in this more concrete way. So this matrix right here gives you a derivative. All right, another thing that you might think about, another thing you might attack with the idea of a matrix is in the world of engineering, there are lots of things that come in the form of waves or just come as a continuous function. So for example, if you're thinking of a wave function, a wave, a sound wave, for example, on your a sound wave, for example, that comes into your speaker or something is going to be continuous. There's always a different vibration that's coming in with that wave. And you have different shapes. And you all probably have been able to do things like make your, see the waveform from your speaker. Maybe it looks something like this, but what is the speaker going to do? How are we going to make a digital representation of this wave? Well, what we're going to do is we're just going to sample at every height and do a sample here, and a sample here, and a sample here, and a sample here. And then we're going to handle this by thinking of this as a very large vector, where our vector is just made up of all the heights, y1, y2, y3, where y1 is that first height, y2 is the second height, etc. And then you would have all of your, you'd have your entire wave mapped out by doing a sample of little heights. And, because of digital technology, we can make these spaces so close together that it's not continuous, but it might as well be, because our ear can't hear the different jumps that happen between these, because they're on the level of microseconds or something. There's such a small interval of time between these spaces that we can't tell the difference. And what's nice is now you could take this waveform and put it in your computer, and then you could alter it. And so you could find ways of smoothing it out. So maybe you want to adjust the pitch or something. You can shift all of these one direction or transform this waveform in another way by doing the transformations we've had. And that would be taking this sound file and hitting it with a matrix that alters it. And this is essentially what's happening anytime you're editing sound in a really fancy booth. Now, of course, the matrices and the way they're formed and the way you're creating it goes way beyond anything that we could probably think about right now. But in a sense, this is what's happening. Okay, so those are the big ideas of vectors. And so the big idea of a vector space is just that a vector space could be, a vector space really is just anything that behaves like a vector. So it doesn't have to be an actual arrow or actually some geometric object. It's just there are lots of things out there that we can think of as vectors, and if we think of them as vectors, then we can do all the same mathematics that we've done up to this point in this semester. Now it's time for me to focus on Markov chains. In brief, what a Markov chain is it's a way of thinking about a vector as a state of being. So we've got some sort of state in which we exist, and then our Markov chain transitions it to a new state. And so Markov chains are great for analyzing things that happen over time, and specifically things that are probabilistic and have probabilities over time. So what you might find is Markov chains work really well for playing a board game. So you have some state, and that is there are different possible things that you can have, and maybe you're definitely in state one, and then you roll your dice, and there's different probabilities for where you're going to be in the second state. So instead of your second state being defined, it's a bunch of places that have probabilities. So we're going to think about this in the game Monopoly, where you roll a dice. And if you're on square one, then there's a 1/6 probability you're on each of the next squares attached to it. Although it becomes more complicated than that, because there are also squares that can send you forward or send you back or send you to jail or things like that. And then we're also going to think about this in terms of the game Chutes and Ladders, or the British call it Snakes and Ladders, where you have your state, and that's which square you're on the board. And then you do a transition, and the transition moves you to a new state. What I'm going to do is I'm going to do each of the Markov chain example problems one at a time. And the reason is those example problems pair up really well with the two application problems that you're going to have to do, and so therefore you can kind of focus on the problem that's connected to the one you're working on the moment. So we're going to start with this first one about whether it's raining or not, and that's going to really give us a good picture of what's going on in the monopoly problem.